You look toward Boötes, and there's a hole in the universe, a region of space so empty it's called the Great Nothing, the Boötes Void. It's a spherical abyss where the stars and galaxies just vanish. This cosmic anomaly is reshaping our most fundamental ideas of reality. We'll see why this void exists against all odds, and what its impossible emptiness reveals. About forces like dark energy, forces that control our fate. What does it feel like to stare into a nothingness wider than you can conceive? The maps were supposed to show a grand design, something orderly. In the 80s, with new surveys and more galaxies catalogued, astronomers started plotting the large-scale structure of the universe. The expectation was a cosmic foam. Matter clustered into walls and filaments, with modest empty spaces in between. That was the prevailing view. It came from our best theories of how gravity shaped everything from a smooth beginning. And the early maps did show that web, a tapestry of light and connection across billions of light years. But then they looked at Boötes, the constellation called the Herdsman. And in the data, it wasn't a filament, it wasn't a modest bubble, it was an abyss. A team led by Robert Kirshner made the declaration. They found a spherical region of space, roughly 330 million light-years across, and it was almost completely empty. To put that in perspective, if our galaxy were a grain of sand, this void would be a hollow sphere wider than North America. Inside that volume, they found only a handful of galaxies, isolated, where the models predicted thousands. This wasn't a small gap, it was a tier. The Boötes void was so vast, so profoundly empty, it challenged the assumption of a uniform universe. Its existence posed a direct question to cosmology. If our theories of structure were correct, how could something this large and this empty ever form? The discovery meant the universe was more than complex. It was fundamentally stranger, more unpredictable than we'd imagined, and it launched a quest. To understand the nature of nothing itself, the scale is just. It's beyond what we can really grasp. Our own galaxy, the Milky Way, is 100,000 light-years across. It has hundreds of billions of stars, and then there's our local group of galaxies with Andromeda. That whole collection, our entire neighborhood, would be just a tiny speck if you put it in the middle of the Boötes void. The emptiness around it, it's on a scale that stops being a distance and just becomes a number. To travel across it at light speed would take hundreds of millions of years. And for almost all of that time, you'd see nothing, black in every direction, no stars, no galaxies, just the cosmic microwave background, that old glow from the beginning of everything. But this void, it's not just big, it's statistically wrong. Based on the average density of the universe, a sphere that size should have tens of thousands of galaxies. That's what the math says should be there, but when they looked with the best telescopes, they didn't find a city of galaxies. They found a desert, a few dozen galaxies isolated. That extreme lack, that's the mystery. It's an anomaly, a bubble of nothing so huge it makes you wonder if we're missing something, if our ideas about how the universe is put together or the rules that built it might be wrong. What could leave a hole that big? Our best theories say the universe should be balanced. It should be symmetrical. The story we tell starts with a smooth beginning. Right after the Big Bang, everything was hot and dense and remarkably even. Just a soup. The only irregularities were these tiny quantum ripples, random variations smaller than an atom. Then gravity takes over. Billions of years, gravity works on those ripples. It pulls matter toward the slightly denser spots. It sculpts, galaxies form. Then clusters of galaxies, they get connected by filaments, vast filaments of dark matter and gas, and the spaces between these structures, they empty out. They create bubbles in the cosmic foam. This whole process has a name: hierarchical structure formation. It predicts a specific pattern, a grand architecture. The cosmic web, and in that framework, voids aren't just possible. They're necessary, they're part of the design, but they have rules. They should be modest. In scale, surrounded by the walls and filaments of the web, the Boötes void shatters that. Its diameter is staggering. Its emptiness is profound. It exists at the very edge of what the standard model allows. It's so extreme it seems statistically almost impossible. So cosmology has this question, a direct and unsettling question: is the void just a fluke? A 1 in a trillion roll of the dice that happened in our neighborhood? Or is its impossible emptiness a clue, a sign written in negative space, telling us that our understanding is wrong? Subtly but fundamentally wrong about gravity or dark matter or the universe's initial conditions. The great nothing isn't just an empty space, it's a question mark. The second principle is dark energy. That's the force that might be actively shaping the void. In the late 90s, astronomers made a discovery. They found the universe's expansion isn't just continuing, it's accelerating. Something is pushing everything apart faster and faster. That something is dark energy. It's not a substance you can see. It's a property of space itself. A kind of repulsive gravity that gets stronger as the universe expands. And that changes the story for voids completely. In the dense parts of the cosmos, inside galaxy clusters, gravity is strong. It holds things together against the push. But inside a void, the gravitational pull is incredibly weak. There just isn't enough matter to fight back. So as the universe expands, dark energy doesn't just stretch the void, it dominates it. It pushes the few galaxies inside even farther apart. It prevents new structures from ever forming. It relentlessly evacuates the space. You can think of the cosmic web as a sponge. Dark energy is the hand slowly pulling it apart, and the biggest, emptiest bubbles in that sponge, like the Boötes void, are where that pull has been most effective. For the longest time, this changes how we see the void. It's not just a static hole, not just a forgotten backwater. It's an active participant, a dynamic entity that's growing and evolving. The Boötes void could be that process in overdrive. A region where for billions of years dark energy has had near total control, clearing out the space with a quiet, unstoppable force. So the great nothing isn't merely an absence, it's a testament, a vast 300 million light-year-wide testament to the most dominant force in the universe today. And the least understood, even in the deepest nothing you find islands. The Boötes void isn't completely empty. Astronomers have found galaxies scattered across it. Just a handful, isolated, alone. They're the loneliest objects in the cosmos. One of them has a catalog number, MCG +01020015. But it's called the loneliest galaxy. It's a dim, dwarf spiral, and from its perspective, if you looked out, you'd see nothing. Blackness for hundreds of millions of light years. No neighboring galaxies, no companions, just the void. Its existence is a puzzle. How did this galaxy form in a place with so little raw material? The standard story is mergers. Small clouds of gas and dark matter collide and combine, building up over time. But in the void, there was nothing to merge with. It was born in isolation. So it must have formed from a rare, solitary seed. A tiny overdensity of matter that existed in that emptiness when the universe was young, and then it had to survive. For billions of years it has persisted, a single candle in an unimaginably large dark room. Its existence tells us something critical, that seeds for structure were sown everywhere. Even in the emptiest places, but in the void, the conditions were wrong for a full community to blossom. Gravity could gather that one seed, but without neighbors to feed on, without a rich environment, it could only grow so much. It became a solitary dwarf, not a grand spiral. Studying these lone wanderers is like finding a single tree in the middle of a desert. It tells you that water is possible there, but only barely. It tells you about resilience, the minimum requirements for a galaxy to exist at all. These isolated systems are pristine laboratories. They haven't been disturbed by collisions or the pull of a massive cluster. They are the universe in its simplest, most stripped-down form. By understanding how they live and die in such a hostile environment, we learn the fundamental rules of cosmic survival. And we have to ask, is their loneliness a tragedy or a testament? A testament to the stubborn, persistent spark of creation, even in the face of the great nothing. To truly map the great nothing, you need to see what isn't there. That's the challenge. Probing the Boötes void, it's not like exploring a dark room. It's more like trying to count fireflies in a stadium from a mile away on a foggy night. The galaxies in there are incredibly faint. Their light is stretched, dimmed by billions of years of expansion, and for a long time our tools weren't up to it. Early surveys used photographic plates. They could only catch the brightest galaxies. It was like using a net with very wide holes to search an ocean. You'd only catch the biggest ones. Any smaller, dimmer dwarf galaxies could have been missed completely, just hiding in the background noise, so the question was left open. Was the void a barren desert, or was it a sparse forest, filled with trees too small for our crude instruments to see? The answer would change everything. Then came the technological leap, projects like the Sloan Digital Sky Survey. It used digital cameras, sophisticated software. It scanned the sky in multiple colors. It created a three-dimensional map of the universe, pinpointing millions of galaxies with new precision. That was like switching from the wide net to a fine mesh sieve. And when they turned this new eye toward the Boötes void, the result was startling. The profound emptiness held. The survey found a few more of those isolated galaxies. But not the thousands that were missing. The void's sparseness wasn't an illusion. It was real. The great nothing was, by cosmic standards, genuinely empty. But each new generation of telescopes pushes further. The Hubble Space Telescope, now the James Webb, they peer deeper into the infrared, looking for the faintest glimmers of ancient light. They ask a new, more subtle question. Could the void be filled with a hidden tapestry of ultra-faint dwarf galaxies, so dim they're virtually invisible? Or could it contain exotic, diffuse forms of matter that don't shine at all? Vast clouds of cold gas, rogue planets. Every advance refines our view. It helps us distinguish between different kinds of nothing. Is it an absolute vacuum, or a place where matter exists in forms we haven't learned to detect yet? The quest to map this emptiness, it's a quest to understand the limits of our own perception. It forces us to build better eyes to stare into the abyss, knowing that each new glimpse might not fill the void, but it will fill our understanding. The universe had a first sound. In the beginning, it was all plasma, a hot sea of particles and light. Gravity pulled matter together, and radiation pressure pushed it apart. That push and pull created oscillations, sound waves moving through the early fluid. Then the universe cooled, atoms formed, and the light was suddenly set free. That moment, the release of the cosmic microwave background, it froze those waves. It made a permanent imprint on where matter would be. Those are the Baryon acoustic oscillations. They set a specific scale, a preferred distance. That distance is about 500 million light-years. It became a blueprint for the largest structures. For the largest empty spaces, the walls, the filaments, the voids, they're all echoes of that ancient rhythm. So the Boötes void, at 330 million light-years across, is one of those echoes. A single, vast note from that first song, but it's an extreme note. It pushes right to the edge of what the standard model predicts. It's like a single tone that's louder and clearer than all the others. That makes the void a precision instrument. By measuring its exact size and shape, cosmologists can test the model. They can ask if this void matches the scale from the cosmic microwave background. Or if it's slightly off, a tiny discrepancy here could be huge. It could mean the early universe's conditions weren't perfectly even. Maybe the density varied. Maybe something in the primordial soup let this one void grow so dominant. Studying the Boötes void is like finding a fossil of exceptional size and clarity. It lets us examine the details of the universe's infancy with a magnifying glass we didn't know we had. So the great nothing becomes a key to the first moments. And the first sounds of everything. If the void is an echo of that first sound, then you have to ask what created the silence for the echo. To get there, you have to go back further. To a moment almost too brief to call a moment, the inflationary epoch. Right after the Big Bang, in a fraction of a second, the universe didn't just expand. It exploded. It grew by trillions upon trillions of times, faster than a blink. This was a runaway stretch of space itself, and it had one job: to iron the universe out. To make it smooth and flat. That's why the cosmic background looks so even. Inflation took any irregularities and stretched them so vast they faded away. But perfect smoothness isn't possible, not on the quantum scale. At that level, reality is a seething foam. Tiny fluctuations pop in and out of existence. And inflation didn't erase those quantum ripples, it magnified them. It took fluctuations smaller than a proton and stretched them across light years. Those stretched ripples became the seeds, the blueprint for everything after. The denser spots became galaxy clusters. The less dense spots became the voids. So in that light, the Boötes void isn't a mistake. It's a prediction, a rare but inevitable outcome. Think of taking a microscopic bubble from that quantum foam and inflating it to the size of a continent. That's what happened. The void could be the imprint of one single, exceptionally large underdensity, a quantum hiccup frozen into space and then blown up to hundreds of millions of light years. It's a fossil, but not from an age of dinosaurs, from an age before atoms, before light, before time had settled into its rhythm. That idea connects two worlds that seem separate. The ghostly, unpredictable realm of quantum mechanics and the vast architecture of the cosmic web. One microscopic fluctuation, born from uncertainty, becomes the great nothing. So the void isn't an accident of later evolution. It's a direct signature of the universe's birth, a message written in negative space, a story that began with a quantum whisper amplified into a cosmic shout. General relativity says matter and energy curve space. A big galaxy cluster warps space so much it bends light, like a magnifying glass. But the Boötes void is the opposite. It's a region of deficit where the density of matter and energy is way below average. And the same equations say this absence also curves space, just in the other direction. Picture space as a stretched rubber sheet. A heavy weight makes a deep dip, bending the sheet inward. But if you could take out a section, make a thin spot, the surrounding material would pull it into a broad hill. A void is that hill. It's a gentle, repulsive curvature. Light going through it doesn't get focused. It gets deflected outward subtly, gravitational lensing in reverse. A negative lens, the effect is incredibly tiny. For one photon, the deflection is minuscule. But the cosmic microwave background, that ancient glow from the early universe, is a sea of photons. When that light has traveled for billions of years, and some of it passes through a void as vast as Boötes, the collective effect becomes detectable. The void leaves a specific, cold imprint on that background radiation. Scientists call it the integrated Sachs-Wolfe effect. It's a fingerprint of the void's gravity, written in the oldest light we can see. By mapping these subtle temperature distortions, astronomers can use the great nothing as an instrument. They're not just observing the void, they're using it to probe the universe. The precise shape and strength of that imprint depends on what's in the void. Is it truly empty of dark matter too, or is dark matter spread out in a diffuse web even there? And most importantly, the effect is dramatically amplified by dark energy. The repulsive push of dark energy makes the void's gravitational hill steeper over time, deepening that cold spot in the cosmic background. So by measuring this imprint, researchers are indirectly weighing dark energy's influence. They're running an experiment on a scale of hundreds of millions of light years, using emptiness as the lab. The void, in its stillness, becomes a lens, a way to see the forces that shape everything. That scientific view is one way to see it, but we've always been unsettled by emptiness. There's this idea across cultures, horror vacui, the fear of empty space. Nature abhors a vacuum, they say, and so does the human mind. We fill blank pages. We decorate empty walls. We tell stories to explain the silent gaps. Emptiness feels like an invitation for chaos, for the unknown to rush in. The Boötes void is that fear made real on a cosmic scale. It's not a darkness hiding something, it's a deeper nothing, a pure absence that defies our need for pattern, for purpose. In art, in literature, the void is a powerful symbol. It's the abyss, the existential dread from confronting a universe without inherent meaning. It's the blank canvas before creation, and the silent emptiness after everything ends. A place this vast and empty does something to your perspective. Our bustling galaxy, with its hundreds of billions of stars, suddenly feels like a single campfire. On an endless frozen plain, it challenges the old idea that we're at the center of anything. Instead, it suggests we might be an accident of matter. Clinging to a rare island of light in an ocean of nothing, the void forces a question. If the universe can contain regions of such profound emptiness, what does that say about our significance? Is our story just a tiny, glowing footnote in a vast, indifferent book of darkness? But this confrontation isn't purely bleak, it's also a source of awe. To recognize the scale of the emptiness is to recognize the scale of the stage. Our existence against that backdrop becomes not less meaningful but more remarkable. The fact that we can perceive this void, measure it, ponder it, that's a profound act. We are the universe observing a part of itself so empty it defies understanding. And in that act of observation, the void transforms. It stops being just a terrifying absence. It becomes a mirror. It reflects back our deepest questions. Why is there something rather than nothing? What does it mean to build a world of light and connection when the default setting of the cosmos appears to be a silent, expanding dark? The great nothing, in the end, tells us more about ourselves than about the space it occupies. It measures the depth of our curiosity and the courage it takes to stare into the abyss and simply seek to understand. The Boötes void isn't alone. It's just the biggest one we know, the largest void we can see, but it's part of a whole structure, a kind of foam where the bubbles are mostly empty. From a great distance, you'd see the galaxies aren't the main thing. They're just the lights tracing the walls and strings of a sponge, and most of that sponge is empty. These voids are like rooms. Most are a normal size, maybe tens of millions of light years across. Our galaxy, the Milky Way, it's on the edge of one. The local void, a smaller emptiness that pushes on our local group of galaxies. It affects how they move, but then there's Boötes. It's a spherical room of such a size, it doesn't fit the normal pattern. So the question is, why is it so different? How did it get that big? One strong idea is that it's not one void, but a combination. Early on, there were smaller underdense bubbles. The universe expanded, and these bubbles grew. Where they touched, the walls between them got thin and broke, like soap bubbles joining into one bigger bubble. Boötes could be from that, a cosmic merger, a few smaller voids coming together over billions of years to make this huge emptiness. That would explain its round shape and its enormous scale. To check this, scientists don't just look at bootes, they count them all. They map the voids everywhere we can see. They measure their sizes, their shapes, whether they're round or stretched or uneven. They see how they're arranged, are voids grouped together or spread out evenly. That comparison is the important part. By understanding the whole family of voids, we learn the rules. Bootes, in its extreme form, becomes a key piece of data. It shows us the upper limit, the biggest size a void can get to under the physics we know and how the universe started. If we're right, voids bigger than bootes should be almost impossible to find. So every new void we discover and measure, it's a test. It either fits the model or it makes us change it. Seen this way, the great nothing changes. It's not just a single, strange emptiness. It's a measuring stick, a ruler in the dark. By putting it next to all its smaller, quieter relatives, we start to hear the whole story. How the universe built itself and what its silent spaces mean. The void's influence goes beyond its own dark borders. It leaves a mark on the oldest light in the universe. That's the integrated Sachs-Wolfe effect. It's a name for a profound cosmic connection. Think about the cosmic microwave background, that ancient glow from the universe's infancy. It travels for billions of years. Those photons journey through the evolving tapestry of the cosmos. When they fly into a massive structure, like a galaxy cluster, they have to climb out of its deep gravitational well. That climb saps their energy. It makes them appear slightly colder. When they fly out of a void, they do the opposite. They roll down a gentle gravitational hill. They gain a tiny bit of energy, making them appear slightly warmer. But there's a crucial twist, and it involves time. If the universe's expansion were driven only by matter, these hills and wells would stay constant. The energy gains and losses would cancel out over the long journey. But if dark energy is at work, accelerating the expansion, the landscape itself changes. A massive void like bootes doesn't just sit there, it grows. Its gravitational hill becomes steeper as dark energy pushes its walls farther apart. So a photon enters the void early and leaves it late. It experiences a net change. It gains more energy rolling down that steepening hill than it would have in a static universe. The result is a specific, subtle signature. A cold spot in the cosmic microwave background associated with that void. It's a fingerprint, a direct imprint of dark energy's work, written in the temperature of the oldest light we can see. Detecting this signal is a monumental challenge. It's like trying to hear a single, soft note in a symphony of cosmic noise. Scientists have to compare the map of the CMB with the three-dimensional map of voids and clusters. They search for these statistical correlations. The bootes void, due to its immense size and profound emptiness, should create one of the clearest such imprints. If we can find its cold signature, it would be a direct observation, not an inference from distant supernova, but a measurement of dark energy's dynamic effect on the fabric of space itself. Using the void as the instrument, so this vast nothingness becomes a laboratory. Its emptiness is the controlled condition. The ancient light passing through it is the probe. And the faint, cold spot we hope to find is the result. It confirms that the dominant force in the cosmos today is not just an idea, it's a tangible presence, actively shaping the architecture of reality on the grandest scale. The void could be a clue to dark energy, but it might also solve another mystery. Where is all the normal stuff? The universe has a matter budget. We know how much normal matter should be there from the Big Bang. That's protons and neutrons, baryons. But when we count everything we can see, stars, galaxies, cold gas, the numbers don't add up. We come up short. Almost half of the normal matter is missing. That's the missing baryon problem, and the emptiest place might be where it's hiding. The idea is this. The missing baryons aren't in bright things. They're not in dense objects. They're thought to be spread out throughout the cosmic web as an incredibly hot gas. Incredibly thin, a plasma so diffuse it's almost invisible to light telescopes. They call it the warm-hot intergalactic medium, the WIM. It should thread the spaces between galaxies. In the filaments and especially in the voids, but detecting it is hard. It's like trying to see heat shimmer from 1,000 miles away. You need the right tools. The perfect conditions, and this is where the Boötes void helps. Its profound lack of galaxies means there's almost no competing light, no bright stars, no energetic quasars to drown out the signal. It's the ultimate dark sky site, so astronomers point X-ray telescopes there, ultraviolet telescopes, not to look at objects, but to look at the space between them. They search for subtle absorption lines, tiny dips in the light from distant background sources, as that light passes through the thin, hot gas. It's like trying to analyze the air in a distant forest by how it filters the light of a single star shining through. Finding this hot plasma in the void would be huge. It would solve the missing Baryon problem, balance the cosmic books, but it would do something more to our view of the Boötes void. It would transform it. The great nothing wouldn't be a true vacuum anymore. It would be revealed as a space filled with a whisper-thin ocean, searing hot, millions of degrees. Yet so sparse that a cubic meter might hold just a single atom. That changes the void from an absolute emptiness to a different state. It's not empty. It's dim, filled with a form of matter so tenuous it defies everyday experience. But it would be the hidden bulk of the normal universe. So the hunt in the void is a hunt for the ghost of matter itself. And if we find it, the silence of the great nothing will have told us where half the universe has been all along. But a mystery this deep, it calls for more than just measurement. The sheer scale of the Boötes void has made some people wonder if our whole framework is wrong. Not just a little off, but fundamentally mistaken. What if the void isn't natural? That's where you get into exotic physics, pure speculation, where science and science fiction start to blur. There's one idea that comes from the multiverse concept. Our universe might be one bubble in a cosmic foam of other universes, each with different laws. In that model, the Boötes void could be a scar, an imprint from a collision, a brushing against the membrane of another universe. In that case, the emptiness isn't about missing matter. It's a place where our reality's rules were subtly rewritten by that contact. Galaxy formation just never began there. It's a staggering thought that the great nothing could be a window not into our past but into a separate cosmos altogether. Then there's an even more speculative idea. It shifts the cause from natural forces to intelligence. The Kardashev scale ranks civilizations by energy use. A Type 3 civilization would harness the power of a whole galaxy. But what would they do with that power? There's a theoretical megastructure called a Dyson sphere. It encapsulates a star to capture all its energy. Now scale that up. Imagine a civilization so advanced, so ancient, that it enveloped not one star, but every star across a region hundreds of millions of light years wide. That entire volume would go dark to our telescopes, a Fermi void named for the paradox that asks where all the aliens are. It would be the ultimate cosmic engineering project. In this wild thought experiment, the Boötes void wouldn't be empty. It would be full, packed with unimaginable technology, humming with controlled energy, completely invisible because its builders capture every photon. It becomes the ultimate answer to the Fermi paradox. They aren't missing, they've finished building, and their masterpiece looks like nothing. These ideas are far outside mainstream science, of course. They lack evidence, they're untestable, but they do something important. They show how an anomaly like this acts as a catalyst. It stretches imagination to the limit. It forces us to see that our current models are just provisional maps. We're still exploring the territory. When something doesn't fit, it doesn't always mean the map is wrong. But sometimes to find the right map, you have to consider every direction, even the impossible ones, so the void's silence becomes a space for creative thought. A blank slate where we project our deepest questions about reality, life, our place in the cosmos. It reminds you that some mysteries are so vast, they don't just ask for an answer. They ask you to reconsider what kind of questions you're even allowed to ask. Isolation changes everything. In the dense parts of the universe, galaxies are always interacting. They jostle, they merge, their shapes get twisted by gravity. But in the Boötes void, the rules are different. A galaxy here can exist for billions of years in total solitude. That creates a kind of cosmic ecology, an ecology of emptiness, and the galaxies that survive here aren't just survivors, they're pristine relics, time capsules. Floating in a silent sea, think of a busy city and then a remote island. In the city, buildings are torn down and rebuilt. The landscape changes fast from outside forces. On the island, change is slow. It's driven by internal processes. A void galaxy is that island, shielded from the chaotic crowds of the cosmic web. Its evolution follows a quieter rhythm. Without frequent mergers, it doesn't get fresh gas to fuel new stars. Its spiral arms aren't stirred by passing neighbors. It ages in peace, but it also ages in a kind of stasis. That makes void galaxies incredibly valuable. They're the control group in the grand experiment of galaxy formation. Studying them lets us ask a fundamental question. What does a galaxy look like when it's left alone, when its story is written only by the gas it started with and the slow, internal churn of its own stars? The answer helps untangle a complex knot. In a cluster, a galaxy's appearance, its shape, its star formation, its size is a product of its nature and its violent environment. In a void, the environmental noise is a whisper. What we see is closer to the galaxy's own, undisturbed character. These isolated systems often show traits that match the quiet life. They tend to be smaller, dimmer, more irregular in shape than galaxies in the filaments. Their star formation is often lethargic, a slow burn, not a roaring fire. Some harbor older stellar populations, stars that have been shining for eons without the disruption of a major merger to create new generations. They're cosmic fossils in a sense, preserving a quieter, more solitary path of galactic life. A path that was far more common in the early universe before the great clusters assembled. So when we point a telescope at a lonely galaxy in the Boötes void, we're not just looking at a distant object, we're running a natural experiment on a billion-year timescale. We're seeing what the universe makes when it works with only the most basic ingredients, in the quietest workshop imaginable. Their existence, their unique properties, are a direct result of the great nothing that surrounds them. They are the ultimate products of void ecology, and in their quiet light, they hold clues to the most internal, most fundamental laws of galactic life. In 1981, Robert Kirshner and his team were looking at galaxy redshift data. They were using the stretching of light to measure distances, trying to map the structure of the universe. They expected to find the cosmic foam, but in the direction of Boötes, the numbers were different. The galaxies just weren't there. Their paper announced a vast spherical void. That was the first formal definition, a hole in the map drawn by the math of missing points of light. It was a landmark, but it came with a question. Were our instruments just not good enough? Were there dimmer galaxies hiding in that darkness? Was the void an illusion? That question drove the next surveys. Projects like the 2-degree field galaxy redshift survey, 2DF, it used a powerful instrument to capture the spectra of thousands of galaxies at once. It built a richer, deeper map, and when they turned this new map toward Boötes, the void didn't fill in. It became more defined. Its borders grew sharper. Its emptiness was confirmed. The handful of galaxies inside were catalogued, isolated specks in a cavern of staggering scale. This wasn't bad data. It was a feature of the cosmos. Then came the Sloan Digital Sky Survey, starting in the year 2000. It revolutionized the field. Its digital eyes scanned the sky, automatically identifying millions of galaxies. It built the most detailed map of the local universe we had ever seen, and it looked at the void again. The result was definitive. Sloan found a few more of those lonely island galaxies. But it did not find the thousands that were missing. The great nothing was real. Its sparseness was not an artifact. It was a fact. Each survey, each leap in technology, reduced the possibility of error. It turned the Boötes void from a curious anomaly into a well-defined feature, an inescapable feature of our universe. These milestones are a quiet triumph. A triumph of systematic, patient looking. Scientists built better eyes, not to find something spectacular, but to confirm a spectacular absence. And in doing that, they turned a mystery into a benchmark. Any successful theory of the cosmos now has to account for this. Any model of how structure forms must explain it. How a region of space 330 million light-years across could end up so empty. The void is no longer just a strange place. It is a standard, a ruler against which we measure our understanding of reality. Our maps of the dark have given the nothing a shape. And in that shape, we find a profound challenge. The gravitational landscape isn't static. It's a flow, and the Boötes void, even in its emptiness, is a major part of that motion. That huge underdensity creates a kind of gravitational hill. The surrounding regions packed with galaxies and dark matter are the valleys. Everything flows downhill. So galaxies on the fringes of the void, including those in our cosmic neighborhood, feel that pull. They're tugged away from the emptiness toward the surrounding masses. That motion is called a peculiar velocity. It's the galaxy's own individual movement on top of the universe's background expansion. You can think of it like leaves on a wide, steadily flowing river. The river's current is the expansion, carrying everything apart, but a local whirlpool or a bend in the bank creates its own currents. Some leaves move sideways or even slightly upstream. That's the peculiar velocity. For decades, astronomers have charted these subtle drifts. They measure the precise speeds and directions of thousands of galaxies. And when they trace those motions backward, they find the sources, the great attractors, the dense superclusters pulling matter in, and the great repellers, the vast voids like the one in Boötes pushing matter away. Our own local group with the Milky Way and Andromeda is caught in this tide. Our peculiar velocity is about 600 kilometers per second. We're being pulled toward the dense Virgo cluster and the even more massive Great Attractor region. But part of that motion is also a push away from underdense regions like the local void and the distant influence of the Boötes void. By mapping these flows with precision, cosmologists are doing something remarkable. They're using the motion of visible galaxies to weigh the invisible. They're creating a three-dimensional map of all the matter in the universe, both seen and unseen. The gravitational influence of the Boötes void, its subtle push, is a crucial data point in that map. It helps constrain where the dark matter must be. How it's woven into the cosmic web, so the great nothing isn't a passive whole. It's an active gravitational entity. Its silence exerts a force. By studying how galaxies move in response to its absence, we're listening to the gravity of the dark. And we learn that even nothing has a weight in the balance of the cosmos. We build universes to test our theories, not real ones. We build them inside supercomputers. These are cosmological simulations, like the Millennium Run. You start with a digital snapshot of the early universe. Those tiny quantum fluctuations are the seeds. You program in all the known laws, gravity, the behavior of dark matter, the push of dark energy. Then you press play. You let it run for billions of virtual years. You watch structure emerge, galaxies form, clusters assemble, and voids appear. It's a digital experiment. You can watch cosmic history unfold in weeks. And these simulations work. They produce a cosmic web that looks like ours. They create voids of all sizes, so it becomes a question of statistics. In this virtual cosmos, built on our best theories, how often does a void as extreme as Boötes show up? Scientists don't run it once, they run it thousands of times, each with slightly different starting points. They create a library of possible universes. Then they comb through it, measuring every void in every digital cosmos, looking for the giants, the outliers. The question is simple. Is Boötes a 1 in 1,000 event in these simulated worlds? Or 1 in a million? The answer tells us something. If a void that scale shows up reasonably often, then Boötes is just a rare fluke, a lucky roll of the cosmic dice in our neighborhood. Our universe, while unusual there, still fits the standard model. But if the simulations almost never produce a void that large and that empty, that's different. That's a quiet alarm bell. It would suggest our simulated universes, built on our current understanding, are missing something. Maybe the initial seeds weren't quite right. Maybe dark energy behaves in a more complex way. Or maybe an unknown physical process is at work, one that empties out certain regions on a scale we haven't accounted for. This is the power of simulation. It turns a philosophical wonder into a measurable probability. It gives us a number, a quantifiable sense of how surprised we should be. So far, the results are intriguing. Some analyses suggest a void like Boötes is rare, but not impossibly rare within the standard model. It sits at the far edge of the probability distribution, but not completely outside it. Other studies argue it's more of an outlier, pushing the limits of what's plausible. This ongoing debate isn't a failure, it's the scientific process. Each new, more detailed simulation with better resolution and more precise physics refines that probability. The great nothing, in its immense silence, is helping us stress test our virtual universes. Every time the simulation runs, we're asking the cosmos a direct question. Are you truly as we imagine you to be, or is your greatest emptiness hiding a secret about your rules? The maps we have now, they're just a sketch. To really understand the void, we need a new kind of vision, and the next generation of telescopes is almost here. They'll see the darkness in ways we never could. They'll turn the Boötes void from a fuzzy outline into a sharply defined laboratory. The first is the Vera C. Rubin Observatory in Chile. Its mission is called the Legacy Survey of Space and Time. For 10 years, it will scan the entire southern sky over and over. It won't just take pictures, it will create a dynamic, three-dimensional movie of the cosmos, catalog billions of galaxies, not just the bright ones, but the faint ones we've missed. For the Boötes void, this is a complete census. It will find every single galaxy down to an incredible faintness, show us the void's true population. Is it a handful of isolated giants, or is it filled with a hidden sea of ultra-faint dwarf galaxies, too dim for our current eyes to see? The Rubin survey will give us the answer. It will define the void's borders with incredible precision, and it won't just look at Boötes, it will map every void in the observable universe, give us statistics. A family portrait of emptiness. We'll finally know if Boötes is a true freak of nature, or just the largest member of a normal, if rare, family. This data will be the bedrock for the next century of cosmology. Then there is Euclid, a space telescope launched by the European Space Agency. Its specialty isn't counting galaxies, but measuring their shapes with exquisite accuracy. Why? To see the invisible hand of gravity. As light from distant galaxies passes by the massive structures of the cosmic web, their images get subtly distorted. Stretched, this is weak gravitational lensing. Euclid will perform this measurement for voids. It will map how the emptiness of the Boötes void itself warps the space around it. Trace the gravitational hill of the void in exquisite detail. This will tell us precisely how much matter, both light and dark, is actually distributed there. Is the dark matter web truly broken, or is it just stretched incredibly thin? Euclid's lensing map will be like an X-ray showing the skeleton of the void. And finally, NASA's Nancy Grace Roman Space Telescope. Its power is in the infrared. It can see through cosmic dust and peer back to the earliest epochs. For the void, this is a search for the smallest and oldest inhabitants. Roman could detect populations of ultra-faint dwarf galaxies within Boötes that are completely invisible to optical telescopes. It could also find isolated, ancient stars, stars stripped from galaxies long ago, floating alone in the dark. These missions work together. Rubin counts the objects. Euclid weighs the unseen gravity. Roman looks for the faintest relics. Their combined data will transform the great nothing. It will cease to be a single, strange anomaly. It will become a rich dataset, a controlled experiment written across hundreds of millions of light years. With this new vision, we will stress test our theories like never before. The void's silence is about to be broken, not by sound but by an avalanche of pure, revealing light. The deepest goal in physics is a single set of rules. A framework that works for the very small and the very large. We have two magnificent theories. Quantum mechanics describes the bizarre, probabilistic world of atoms and particles. General relativity describes the graceful curvature of space-time by mass and energy. Both are stunningly accurate in their own domains, but they are incompatible. They speak different mathematical languages, and at the extremes, like inside a black hole, or at the very beginning of the Big Bang, both theories break down. We need a new theory, a theory of quantum gravity, something that stitches these two worlds together into one seamless fabric of reality. It is perhaps the greatest unsolved problem in all of science. And strangely, the emptiest place we know might one day offer a way in. The Boötes void presents a unique environment. It is a region where the average density of matter and energy is almost zero. The gravitational field is incredibly weak and uniform across vast distances. It is, in a sense, the closest thing we have to a pure, undisturbed fabric of space-time on a cosmic scale. In such a pristine environment, any tiny deviation from the predictions of Einstein's general relativity would stand out. It would be like trying to hear a single, pure note in a silent room, versus trying to hear it in a roaring stadium. Some theories of quantum gravity, or modified gravity, predict subtle effects that could accumulate over enormous scales. Imagine a beam of light traveling across the 300 million light-years of the void. According to strict general relativity, its path is determined by the smooth, gentle curvature of that emptiness. But if space-time itself has a quantum graininess, a fundamental fuzziness at the tiniest scales, that journey might be different. The light could scatter in a minuscule, cumulative way. Its polarization, the direction its waves vibrate, might rotate by a tiny, predictable amount. Or the void's expansion rate might not perfectly match the predictions of our standard model with dark energy. A discrepancy, even a breathtakingly small one, could be a fingerprint. The fingerprint of physics beyond Einstein. Currently, such effects are far, far beyond our ability to measure. The predicted signals are whispers in a cosmic hurricane of noise. But the trajectory of science is one of increasing precision. Future observatories, perhaps combining the power of gravitational wave detectors with exquisitely sensitive measurements of the cosmic microwave background, could one day achieve the needed clarity. They could use the Boötes void as a natural interferometer, a hundreds of millions of light-years long laboratory. By studying how the oldest light propagates through its emptiness, or by tracking the precise motion of its few isolated galaxies over decades, we might detect an anomaly. A tiny crack in the elegant edifice of general relativity. This transforms the meaning of the void completely. Its profound emptiness is not an end, it is a beginning. It becomes a potential window, a window into a regime of physics we cannot yet recreate or observe anywhere else. The quest to understand the great nothing could, centuries from now, become part of the quest for a theory of everything. In its vast, quiet darkness, we might one day find the first faint glimmers of a deeper unity, a hint of how the universe truly works from the quantum foam to the cosmic web. The great nothing isn't just in observatories, it's for anyone who's looked up and wondered. That shared curiosity drives some of the best astronomy today. Like Galaxy Zoo, it started with a simple problem. The Sloan survey had 1 million galaxy images, too many for one team, so they asked for help. They asked the public, people with no training, to go online and look. To answer simple things, spiral or ellipse, does it look strange? The response was huge. Hundreds of thousands of people, all sorts of people, using their breaks, their evenings, to sort the cosmos. That's citizen science, and it changed things. All those human eyes helped map the cosmic web in new detail. They found rare things computers missed. And their work helped trace the edges of voids, like the Boötes void. Each classification is a small part of something big. It turns data into a personal find. You look at a galaxy, call it a spiral, and for a moment you're an astronomer. You're adding a point to the map of everything, and the void story does more than science. It becomes a bridge, a hole in the universe. That phrase catches you. It grabs the imagination where data can't. Writers, teachers, they use that mystery as a door. It's a tool to explain dark energy, cosmic structure, the Big Bang. You start with that image, a huge spherical emptiness, and it pulls people into the deeper questions. How did this form? What does it mean? That shared wonder matters. It builds public support for basic research, the kind that looks for understanding, not profit. It shows that studying an abstract dark patch millions of light years away isn't just academic. It's part of a bigger story, a story about where we came from. The same forces that carved the Boötes void also shaped our local group of galaxies, our home. Mapping the emptiness is like tracing our cosmic family tree. We're learning the conditions that made us possible, so when a volunteer classifies a galaxy on the far side of the void, or someone watches a documentary, they're not just watching science. They're connecting to it. It's a reminder the universe is a shared inheritance. Its biggest mysteries are an invitation for everyone to look deeper, to ask, and to marvel that we can even try to find answers. For a long time, there's been this idea in cosmology, the Copernican principle. It says we aren't in a special place. Earth isn't the center of the solar system. The sun isn't the center of the galaxy. Our galaxy isn't the center of anything. We're typical observers in a uniform cosmos. That's more than philosophy. It's a practical assumption. It lets cosmology work. We can look at our local patch of the universe and assume it's representative of the whole, that the laws of physics are the same everywhere. That matter is roughly evenly distributed. This assumption of large-scale homogeneity, it's the bedrock for our maps and models. The Boötes void tests that bedrock. It asks a sharp question: how likely is it to find a void this big, right where we're looking? Scientists run the numbers. They take models of the cosmic web, the expected distribution of void sizes, and they calculate the probability. If you took a random spherical survey of the universe, 330 million light-years wide, what are the odds it would be as empty as Boötes? 1 in 100, 1 in 1,000, or 1 in 1,000,000? The answer carries weight if the probability is reasonably high. Then the void is just a rare feature, part of the cosmic tapestry, not a threat to our assumptions. We just live near a large bubble, but if the probability is vanishingly small, a statistical outlier of extreme rarity, then the Copernican principle trembles. It would suggest our local volume isn't typical, that we might be in a special place. An unusually underdense region on a scale we hadn't imagined. This isn't about geocentrism, it's about a potential flaw in our assumption of large-scale uniformity. Maybe the universe is more lumpy on the very largest scales than our models allow. Maybe the seeds from inflation weren't as evenly distributed as we thought. The void forces this reckoning, a humbling possibility that our cosmic address, far from being mediocre, might be in one of the grandest empty rooms in the entire observable universe. And if that's true, what does it mean for everything we think we know about the cosmos beyond our walls? Patterns repeat. Across the cosmos, across different fields, the cosmic web with its bright nodes and dark voids isn't unique. It echoes. In our brains, billions of neurons form dense clusters, linked by filaments surrounded by quiet tissue. You see it in the roots of ancient forests, in human relationships, in digital networks. These are all complex systems, and complexity science gives us a new way to see the Boötes void. It changes the question, not what the void is, but what it does in a larger system. In any resilient network, the empty spaces aren't failures, they're necessary. They provide stability, they prevent overcrowding, they create pathways for flow. In the cosmic web, voids are the insulating gaps. They keep galaxy clusters distinct. They act as buffers, letting filaments channel gas across huge distances. If the universe were packed uniformly with galaxies, it would be chaotic, unstable. Collisions would be constant. The voids create separation. They give the structure room to breathe, to evolve. So analyzing the cosmic web's topology, the shapes, the sizes, the connectivity of its voids becomes an exercise in geometry. Scientists use tools from network theory. They measure a void's roundness, how many filaments connect to its walls, the distribution of smaller bubbles inside it. These metrics can be compared to a neural network, a social network, an ecological web, and the finding is, despite the vast differences in scale and substance, these networks often share common mathematical signatures. They follow similar rules of growth, of optimization that suggest something. The great nothing in Boötes might not just be a product of cosmic physics. It could be an inevitable outcome of a more universal principle, a principle of efficient organization in complex systems. When matter and energy self-organize under certain constraints like gravity on dark matter, this web and void pattern may simply be what emerges. It's a pattern that balances connection with isolation, density with emptiness. From this view, the void transforms. It's not just a cosmological anomaly, not just a dark energy lab. It becomes a data point in a grander inquiry, an inquiry into the fundamental patterns of complexity. The same organizational logic that shaped the void might be at work in the growth of a city, the spread of an idea, the firing of a thought. By staring into the largest emptiness we know, we might be glimpsing a deep, recurring blueprint for how things come together and how they fall apart across all scales. That emptiness has a future. It's a future of growth, relentless growth. In a universe with dark energy, the Boötes void isn't finished. It's active, it's evolving. Its fate is tied to the expansion of space, the expansion that's accelerating. Dark energy pushes the cosmic walls apart. So the void expands. It expands faster than the average. The few galaxies inside it, they'll be pulled even farther out into deeper isolation. The sparse gas inside will thin out, become more diffuse, making new stars virtually impossible. And over tens of billions of years, this just intensifies. The void's volume grows, its borders get more distant. More faint, but the Boötes void isn't growing alone. It's part of a network. Other voids are around it, smaller bubbles in the cosmic foam. As the universe expands, the filaments between them stretch. The walls stretch, they become tenuous, and eventually they may break. The boundaries could dissolve, and the voids would merge, like soap bubbles coming together into one giant bubble. The Boötes void could join its neighbors, creating a single, incomprehensible expanse, a supervoid, on a scale that dwarfs what we see now, that leads to a vision of the far future. A profound one, maybe an unsettling one. Billions upon billions of years from now, dark energy dominates completely. Galaxy clusters become isolated islands. Their gravity is the only thing holding them together against the stretching tide. The spaces between them, the voids, they'll have one. The cosmic web, that tapestry of light and connection, gets torn apart. The bright nodes drift apart into an ever-cooling, ever-darkening emptiness. The universe becomes a place of profound solitude, vast dark oceans with only rare, dim archipelagos of stars. So understanding this void, the Boötes void, gives us a preview. It's a natural laboratory, showing us the end game of cosmic structure. In its growth now, we see the early stages. Stages of a process that will eventually affect all of space. That vision shifts the perspective. The void isn't just a static feature, not of our current universe. It's a harbinger, a glimpse into a future where emptiness is the default, where islands of light are the rare exception. This long-term view, it invites a quiet reflection. It asks us to consider the transient nature of cosmic community and the deep, slow forces, the ones quietly reshaping the architecture of everything. The Boötes void is a good example of how mysteries can get bigger in our minds, but the real thing is more interesting. So first, it's not a hole. You couldn't fall through it. It's more like a desert, a huge region where the galaxies are just very few and far between. The space is still there. The same physics applies. It's just that the density of luminous matter, the stuff that shines, is extremely low. The canvas is there, but the painter barely touched it. And second, it's not a perfect vacuum. It looks empty to our telescopes, but it's almost certainly filled with the invisible structure. Dark matter is probably there, a faint web, and astronomers think it contains the missing baryons, a superheated, incredibly thin gas, so diffuse that a cubic meter might hold just one atom. It also has those few lonely galaxies, so it's not nothing. It's a different state, a place where matter is quiet and spread out. Finally, the Boötes void isn't evidence against the Big Bang. It's the opposite. Its existence is a challenge that helps refine what happened after. The standard model of cosmology, which includes the Big Bang and dark matter, actually predicts large underdense regions should exist. Maybe not this extreme, but they're predicted. The void isn't breaking the rules, it's testing their limits. It makes us ask if our models of how gravity shapes the universe need small adjustments. Is it a rare fluke or a sign of new physics? That's the active question. By clearing away the myths, you ground the awe in something solid. You move from a vague idea of a whole to a precise appreciation for a cosmic laboratory. That doesn't shrink the mystery, it deepens it, because now you're not staring into an imagined abyss. You're looking at a specific, profound feature of reality. One that holds real clues about the forces that built everything. The truth of it is stranger and more illuminating than any simple story. No one was looking for a hole in space. The Boötes void was an accident, a gift inside the data. In the 1980s, astronomers were doing broad surveys of galaxy redshifts. They wanted to map the structure of the cosmos. The filaments, the clusters, they were looking for what was there, and in the direction of Boötes they found an absence, a spherical region where the pinpoints of light just weren't. Robert Kirshner's team wasn't hunting for voids, they were charting the territory, and on that chart they saw a blank spot, a blank spot so large it couldn't be ignored. The big cosmic mysteries often arrive like that, not with a fanfare, with a quiet anomaly in the numbers, a place where the story goes silent. This pattern keeps happening. The cosmic microwave background. Arno Penzias and Robert Wilson were radio engineers. They had a persistent hiss in their antenna, an annoying noise. And that noise was the echo of the Big Bang. They were looking for a clean signal and found the oldest light or dark energy. Two teams were measuring distant supernova. They wanted to see how fast the universe was expanding. They thought it would be slowing down. The data said it was speeding up. They found the opposite of what they wanted. And it changed everything. In every case, it came from listening to the data, not forcing it to match an expectation. The Boötes void belongs to that tradition. It's a monument to open-ended exploration, to mapping without a rigid checklist. It shows you something. The path to new understanding isn't straight. It's a meandering line, guided by curiosity, sharpened by surprise. You build the best instruments you can, you ask clear questions, and then you have to stay humble. You have to listen to the results, even when they whisper something unexpected. Finding the void was serendipity, but that moment needed years of work first. The surveys were the canvas, the anomaly was the signal, and the prepared, curious mind connected them. It celebrates a style of research, mapping for its own sake. Not for an application, but because we want to know what's there. That kind of exploration builds the charts all future voyages need. So the story of the great nothing is also a story about how we know anything. The universe doesn't have to fit our models. It's richer, stranger, more inventive. The cosmos is full of surprises waiting in the data. They show themselves not to people who want confirmation, but to those with careful, patient attention, people willing to say, "That's odd," and then spend decades asking why. The void's profound silence started as a statistical blip. A gap in a catalogue of light. Someone noticed, someone took it seriously, and it became a window into the deepest forces shaping reality. The next big discovery might not be an emptiness. It might be a subtle spectral line, an unusual motion, a tiny excess of heat. It'll be hiding in plain sight, in data collected for another reason, waiting. For a curious mind to look at the map, to see the blank spot, and to understand the blank spot is the message. The oldest light we can see has a faint, cold fingerprint. It's the cosmic microwave background, and it's not perfectly smooth. There are tiny variations in temperature, little spots that are slightly warmer or cooler. Those are the seeds that eventually grew into galaxies, clusters, and into voids. For a while now, some researchers have looked at the map of that ancient light, and then at the map of the Boötes void. They've asked a pretty bold question. Could that particular emptiness, that huge void, actually be casting a shadow on the first light? It comes down to a specific cold spot in the microwave background. A region that looks a little cooler than the glow around it. The statistical significance of that cold spot has been debated. Is it just random noise in the data, or is it something real that needs explaining? One explanation that's been proposed is the integrated Sachs-Wolfe effect from a supervoid. So, photons from the cosmic microwave background pass through an immense underdensity, like the Boötes void. They roll down a gravitational hill. In a universe with dark energy, that hill actually gets steeper over time. The photons gain a net amount of energy, which makes them appear, strangely, a bit colder at the specific frequency we measure. It's a tiny effect, but for a void that's hundreds of millions of light years across, the total shift could, in theory, create a detectable cold patch on the microwave sky. What's really interesting is the alignment. Some analyses have suggested the direction of the Boötes void lines up with one of these anomalous cold spots. The idea isn't that the void caused the cold spot from the very beginning. but that its huge gravitational presence over billions of years has left a mark on the light that traveled through it. Now, this is highly speculative. The correlation is weak. The measurement is right at the edge of our statistical confidence. A lot of cosmologists are skeptical. They think the alignment is just chance in a sky full of fluctuations. But chasing this connection isn't a wild guess. It's observational cosmology pushed to its limit. It represents a specific, testable prediction of our standard model with dark energy. If a supervoid like Boötes really exists, and if dark energy behaves the way we think, then it should imprint a specific signature on the cosmic microwave background. Finding that signature would be a huge confirmation. It would directly link the gravitational influence of the largest structures we see now to the oldest light we can observe. It would be a direct detection of dark energy's work written across the sky, so the research keeps going. New, more precise maps of the microwave background from observatories like Planck are being scrutinized. The three-dimensional location and exact shape of the Boötes void are being refined with surveys like Sloan. Scientists cross-correlate these huge datasets, looking for that faint, telling signal. Even a null result is valuable. It puts tighter constraints on our models. It tells us the limits of the effect, but the possibility, however slim, of a confirmed connection keeps the search alive. It turns the void from something we study into a tool for a deeper probe. We're using its immense silence as a lens to look at the first light of time. And in that delicate, cold spot on the map of creation, we might one day read the undeniable signature of the great nothing. The void is immense. It's a space measured in hundreds of millions of light years. Our whole story fits into a tiny corner of it, that feeling, the cosmic insignificance. It's humbling, jarring, even all of human civilization, every empire. Every work of art, every life, it all happens on one fragile world, orbiting one star among hundreds of billions, in a galaxy that's just a speck against the great nothing. Our local cluster of galaxies, our whole neighborhood, would be lost in that darkness. The void shows us an empty space, but it also holds up a mirror. And the reflection is vanishingly small, but that realization doesn't have to be an end. It can be a beginning, a kind of liberation. When you take in that scale, the petty divisions, the conflicts that consume us, they're revealed. They're local phenomena, temporary dramas on a tiny, isolated stage. The universe, in its vast and silent architecture, is indifferent to our borders. Our ideologies, our histories, that indifference isn't cruel. It's a clarifying truth. It strips away the illusion. We are not the protagonists of the cosmos. We are participants, and that shared participation on this one planet becomes the most important thing. This is where the void's lesson turns, from chilling to unifying. Staring into that abyss can forge a shared humanity. Carl Sagan called our world a pale blue dot, a mote of dust in a sunbeam. The Boötes void frames that dot within an ocean of darkness. An ocean so vast it defies poetry. From that vantage point, all of us, every person, every culture, every living thing, we're aboard the same tiny vessel. Sharing this one rare island of complexity and light, in a sea of silent simplicity, the conflicts that seem all-consuming from within are invisible from the perspective of the void. What is visible, what becomes precious, is the island itself. The fact that here, against astronomical odds, there is warmth, connection, story. So the great nothing, in its absolute indifference, performs a strange alchemy. By showing us the scale of absence, it throws into sharp relief the fragile miracle of presence. It highlights the preciousness of everything it lacks. Life, consciousness, love, art, the intricate dance of ecosystems, the warmth of a sun. The void has none of these things. It is the pure, unadorned canvas. We are the unlikely, vibrant painting. This perspective doesn't diminish our story. It reframes it. it asks us to see our world not as a given but as a gift. A temporary, dazzling spark in the long dark. That reflection brings a quiet responsibility. If our cosmic address is so rare and our moment of awareness so brief, then what we do with this pale blue dot matters immensely. Not to the universe, which will remain silent, but to us, to all the life that calls this dot home. The void's message, in the end, might not be about our smallness, but about our singularity and the profound duty that comes with it, being the only part of this immense cosmos, as far as we know, that can look upon the darkness and choose to cherish the light. The Boötes void is one question with many answers. We've called it a statistical fluke, a dark energy amplifier, a quantum fossil, a gravitational lens. Each one shows a piece of the truth, but none of them explain the whole thing. The real power is in putting them together. It asks you to hold several ideas at once, even if they seem to contradict. This emptiness isn't just one problem for cosmology. It's a convergence point where the physics of the very large meets the history of the very old. Where dark energy's push meets the absence of gravity's pull. Where a random quantum fluctuation meets the inevitable structure of a network. To understand it, you have to weave these threads. The best explanation isn't one dramatic reveal. It's a layered story. It starts with a rare seed, a primordial underdensity, a little larger than average, imprinted by inflation's quantum magnifying glass. Over eons, this region expanded with the universe, but its emptiness made it a weak competitor. As the cosmic web formed elsewhere, this bubble was left behind. A backwater, then dark energy took hold. In this already underdense place, with little gravity to resist, dark energy's repulsive push found its purest expression. It accelerated the void's growth, actively evacuating it further, stretching its borders and isolating the few galaxies inside. And at the same time, the complex dynamics of the expanding cosmic web likely let this void merge with smaller neighboring bubbles, creating the colossal sphere we see. It's this combination, a rare start amplified by the dominant force of our era and sculpted by the web's architecture, that likely made the great nothing. This synthesis changes the void from an outlier into a keystone. Its existence doesn't break our cosmological model. It stress tests it. It forces the model to account for extremes, to prove it can generate such profound emptiness as a natural outcome. Every new observation of the void, its precise size, its effect on ancient light, the motion of its lonely galaxies tightens the constraints on our theories. It refines our numbers for dark energy. It sharpens our picture of inflation's initial conditions. It helps us map the invisible dark matter web, so the study of nothing becomes essential to understanding everything. The void isn't a bizarre footnote anymore. It's an integral chapter, a chapter written in negative space, asking us to read not just the ink, but the empty page itself. The Boötes void, the great nothing, it's this huge spherical emptiness, a monument but not made of anything, made of absence. It makes you rethink the fabric of reality. We've looked at it as a cosmic laboratory, a gravitational lens, a fossil from the very beginning, a canvas for our questions, and what it teaches is that what's missing can be as informative as what's there. The void defines the cosmic web. Its lack is essential to the story. Our exploration shows a feature that consistently challenges our best models. It pushes cosmology's math to its limits. It asks if our assumptions about uniformity and scale are really complete. But that challenge isn't a failure. It's the engine of science. The void's mystery has driven leaps in technology. Building more sensitive telescopes, simulations with unprecedented detail, all to better see the dark, and beyond equations and instruments, it provokes a deep philosophical inquiry. It holds up a mirror. It reflects our staggering smallness and our remarkable ambition to comprehend these impossible scales. As we keep mapping the darkness with greater precision, remember this. The Boötes void isn't an endpoint for curiosity. It's a beginning, a gateway. Its silent expanse points toward deeper questions about dark energy, the quantum birth of the cosmos, the ultimate fate of all structure. It reminds us the universe is far stranger, more inventive than any story we've told. So let this mystery inspire wonder. This great and beautiful nothing. Next time you look up at the night sky toward Boötes, know you're gazing toward one of the cosmos's most profound puzzles. A silent, spherical question, hundreds of millions of light years wide, and wonder what other profound nothings are out there, what other majestic absences waiting in the depths of space. The map is never finished, the story is always being written, and our shared curiosity is the pen.